Welcome back, everybody. I hope everyone's caffeinated. Our next talk will be by Sergio Pintaldi from the Sydney Informatics Hub at the University of Sydney. And he's going to talk to us about scalable transient detection pipeline for the Australian SKA Pathfinder VAST survey. Thanks very much, Sergio. You have the floor.
Welcome, everybody. I'm Sergio Pintaldi from Sydney University, and today I will be talking about a scalable detection pipeline for the Australian Pathfinder VAST survey data, aka VAST pipeline, just to make it easy. I would just want to say that I'm part of a team of 4 people, so Adam and Tara from the University of Sydney, and then Andrew and David from the University of Wisconsin-Milwaukee from the United States. So and just try to go very quickly through the slides so we can get to the demo of the pipeline. Just a quick introduction of the ASKAP telescope. So it's the precursor of the SKA, so the square kilometre array. Essentially is a telescope that will produce like a high density, very big images, like 800 megabytes each of the feed files, so 30,000 pixels. And so on. So we're expecting like a huge amount of data to be processed in a timely manner. Regarding the VAST is the search for variable slow transient. And as you can see in the map, the orange areas are just the pilot survey. And we were able to process, and I'll give you a little bit of detail later on. Some of the challenges with the ASKAP data essentially are the scalability. So we're dealing with a huge amount of data. For example, just the pilot data are something like around 10 terabyte or images, 900 something images, or the order of 10, 12 terabyte of data. So essentially we have a lot of images and we need to process them pretty quickly because people need to look at the data and the result, because there is a lot of issue, like a lot of false positive, for example. And also we need to compute a lot of stats, for example, calculating like variability metrics and then visualize like curve. So essentially we just at the end, you know, like the user need to look directly at the light curve to detect the transient. So a little bit of the tool that are out there. There are already some tools that are doing this transient detection. So some of them are like a custom code developed by students or researcher, and there was like also an old VAST pipeline developed at the University of Sydney and UTS, so University of Technology of Sydney. And also there is the most famous one, which is the TRAP, which is the transient detection code base developed by the LOFAR guys, which is accompanied by the Banana interface, which is essentially a web app. We tried at the beginning using TRAP, and Adam, for example, modified him to ingest data straight for the ASKAP, straight from the ASKAP data. And but we find it hard to scale, and there are some issue, like, you know, is a bit old legacy code. Some of the dependencies will be hard to deal with. It's Python 2.7, and all the association were done in SQL. But at the same time, TRAP is really great because it's besides being well known on the community, its association logic is quite robust, and is currently using in LOFAR and NIRCAP telescope, if I'm not wrong. Anyhow, we decided to develop the new VAST pipeline, you know, taking an example. So we design it in a way where we reuse some of the ideas from previous pipelines. So, for example, some of the folders data structure of the pipeline run, but we decide to use more modern tools, like we move, for example, we move the association stage outside the database. So before, for example, TRAP does everything in SQL statement, but we move it outside using pandas, Python pandas and AstroPy. So essentially the VAST pipeline that we build is a Django web app where both the web app and the pipeline itself that can be run via command line are united in the same code base. So we have like a backend, as I said, is Django, Pandas, and AstroPy mainly, and we use Dask to scale up the computation, and then a front end with a Bootstrap template, Aladdin, JS9, Bokeh, and so on. The main storage system are the database, Postgres, and we also write data to Parquet files for post-processing and distributing the data itself. Let's have a look at the architecture. So essentially, we previous existing tools like Trap and the old VAST pipeline, they were in older version of Python packages, but we decided to upgrade everything and make use of the latest feature, for example, latest feature AstroPy. So we adopt a very simple relationship between images and sources. So essentially, we defined as measurement like single sources that were taken over at a specific point in time, and then we associate those measurements into sources, which is a single astronomical object. Okay. Some of the steps we do, so the pipeline itself doesn't have a source finder. So because we plug in downstream for the CSRO pipeline, which CSRO operate the ASKAP telescope, and then he manage the raw data, the ASKAP raw data. So he give us like essentially 4 files, the fit files of the image. So the source catalog, so with the measurement, the extracted measurement from the images, and they use this CELAVI source finder, the noise data and the background data. So what we do, we just ingest all of these 4 files for each image object, let's say, and we clean them. For example, we do some, we clean up the errors using Condon method. Then you can choose to process the data in to associate the measurement into 3 modes: basic, advanced, and the Reuter. And we'll see a bit later what these modes are all about. We calculate these new sources feature, and we do force extraction as well. So if something was not detected, you can turn this on off, like. And at the end, we just calculate so many metrics like the eta and we do also like so the variability metrics, and we do a tube epoch analysis, and then we output everything to a nice folder, like a folder structure per pipeline run with Parquet files, so you can scale up then this later on, and as well in the Postgres to serve the web app. Some of the feature, like for example, the pipeline is association. As I said before, there are 3 methods: basic, advanced, and Reuter. We make use of AstroPy function. So for the basic, we use like the closest match, and we'll find the closest match to the current measurement or source measurement. And but in the advanced and the Reuter method, we make use of a search around the sky function, where you can actually find multiple sources, like source and measurement that are close to each other, and we record them as related. And beside that, we implement we calculate the Reuter if we choose the method of association, and then we use the Reuter radius that you input, or the radius in general, that to filter out all the sources, all the measurements that they don't need to be associated with each other. Beside that, we use the same logic of the Trap code base, so we do a 1-to-1 association, 1-to-many, and many-to-1. As I said before, we have this feature called new sources. So essentially, for example, when we're processing 4 images, 1, 2, 3, 4, and then we for example, for the source B, in this example, we realized that B was not detected in image 1 and 2. So we force extract the measurement from those images, and then we flag as a new, and then we use a sigma parameter just not to flag all those cases. And then also we force extract forward in time. For example, in image, this source A was not detected in image 4, so we force extract. So the force extraction code is a custom code that we don't use any of those community codes like AGN or others. Let's have a look at a quick demo. So let's see, hopefully the time's not too bad. So this is a local pipeline in my local.
You have 2 minutes.
Okay, that's right. So I'll be quick. So we log in and we use like a social login. So we GitHub, so all the VAST, the ASKAP VAST community can log in. So we have a production environment. This is just the local. So I'll just give you a bit of an overview. So you can filter to pipeline run. So let's open this one in where I process 100 images. So you can see like the sky region, some more general statistics. So you can have a look at the config file. You can even modify this config file. You can even run the pipeline from this interface. So there is like the log file. We can have a look at the single images. We make use of Adeline Light. There is commenting. There is single measurement view where there is a postage stamp. Also like comments and stuff. And the most important part is the source query. So there is a very complex query where you can filter out by number of data points and so many other parameters. But let's have a look at one of the sources. So let's order by data points. So these are 36 data points. And this is actually the sources with the light curve. So there are 36 data points, but because they are like overlapped with each other, in fact, we have like, external query catalogs, and these all the 36 postage stamp. So essentially is all of these, you can even star your source and put in your favorite. So in concluding, I just want to say that we've developed this modern data platform to scale up the ASKAP data. We were able to process. We have a production platform hosted in Nimbus, which is a CSRO. So it's under the POSI supercomputer. So where all the ASKAP community can log in, and this is a screenshot of the production environment. So we process the full VAST pilot survey in around 13 hours. So this is like 900 images, 8 million of measurement. They've been associated. This is with like a full. So this is from scratch. So this time include like uploading to database, force extraction, and I think we use the router. So we just use all the functionality of the pipeline, and this is like the spec of the machine. So hopefully this pipeline allowed for faster search for transient, so enabling like faster science. And but at the same time, there are some challenges, like we need to improve the code. There are some parts like the database upload are not very efficient. We need to scale up the database to serve the web app, because with these millions of data, and then tuning the DAS cluster, and then involve more the community to make sure that people will use this and find it useful. So that's pretty much it. So if you have any question, you can contact me on via email or on Discord or anyhow. Thank you.
Thanks very much, Sergio.
Sorry, it was a bit dense.
We have a question. First question from Francois Bonarel. Do you intend to publish alerts using VO event infrastructure or something else?
I don't think so, because this is more like a real-time. So the question is for me real-time transient detection, but at this stage, because also we came downstream from the CSRO pipeline, we potentially can do real-time, because you would just scale up the DAS cluster and scale up the database and make sure that have like queues and these kind of things. But Yeah, so we don't provide this alert because this is not a real-time pipeline, even though it could be or at least near real-time. I wouldn't say real-time.
Thanks, Sergio. Another question from Robert Nikuta. How quickly do you need to run the pipeline, and how many associations do you perform? For example, how many per night?
So, well, I don't really know because this ASKAP telescope is still in piloting survey. So that survey, like there was a survey of 900 images. It was they didn't come every day. I think some of them come every couple of days, and then for a month they didn't know there was no images. So, but potentially this pipeline, you know, its architecture enable for fast processing, because some of the computation using the dust cluster are using most of the computation, heavy computation using the dust cluster. You just scale up the cluster. But yeah, so we don't really have a time at this stage.
Okay, thank you. I think if we can maybe move any further discussion into the talks channel. Let's thank Sergio again.